Hello, hello. My name is Ugo. So this is my solution for, or my explanation, evaluation, or review process of the power of three elite code problems. So, um, yeah. Let's go back here. So let's look at the problem, or I guess I could read it from here. It's probably better from here because it has more details, kind of. Um, So we're given an integer n, and we're supposed to return true if it is a power of 3 or false otherwise. So power of 3 specifically means, let me type it right here. It's not talking about x to the power of 3, it's talking about 3 to the power of x. So, um, so is it, so this is an exponential function. It's not a cubic function. Um, so because of that, we kind of have to remember, like, okay, what are the properties of exponentials? And actually, I could just let me just open up Desmos real quick. So exponentials, can I just do e to the x actually? Yeah, e to the x. So e to the x, let's just look at an exponential. They'll infinitely approach zero, but never actually get to it. So that's an important thing to know considering the input values that are possible. So we're given the constraints of -2 to the power of 31, or the range between -2 to the power of 31 to 2 to the power of 31 minus 1. So because we're given that range, we know that we may be given values that are down here in the negatives to check if that is a possible value for the exponential. And because of exponential's property of never going to zero, or like infinitely approaching zero but never actually getting to it, it's saying it here, but that's because it's just infinitely approaching it. It doesn't ever actually get to zero. So knowing that, we can create a base case where if we're given a number that is zero or negative, then we know that it is false immediately because that is not possible. And I mean, we could see this here with the examples that they gave us. They gave us, I mean, even if they didn't give us that, like if we had this here, just knowing that that will never happen is important because we could create a base case that just returns false in that case. And then we can move forward from there. And so my initial solution for this, or initial thought process was, well, technically, it's not naive after looking through it or realizing the problem with my final solution. Um, but the initial solution I thought of was just multiplying a number 1 by 3 repeatedly until we get to a point where we either overshoot or undershoot, or whether we either get to the number or overshoot the number. And that solution would work. I'm pretty sure if I go to submissions and look at like the most efficient ones, it kind of does something like that. Modulo 3. Modulo 3, just keep dividing. Okay, so this is kind of the same thing. I mean, it's just different. Probably better space complexity wise because you're not really creating the integer to store the increasing value. Instead of just dividing the number that you currently are given. So that was the initial solution I thought of, and I thought, okay, maybe I could improve that with like a list. I went to go eat, I came back, and then I realized I don't know what I'm thinking. If it's an exponential and we're just looking to see if it's a power of 3, we're looking for if x is a number that's an integer, we could just use the log base 3 function, or a log of base 3. So I tried that. And that was, theoretically, it would work right. So if we just did this and then checked if it was an integer, it would normally work right. But because we're working with computers, we have floating point errors, or precision errors, basically. So that is where I realized, okay, maybe the iterative solution, although it's a little slower technically, um, or should be normally like a little slower, uh, even though it is technically supposed to be slower, the problem with it or the problem with this solution specifically, is that you have that floating point precision error, where cases like 243 would give you a result of 4.99 repeating until, I guess, whatever the value can be, how many numbers of that can be stored, rather than 5. So it's actually 5, but it just gives you 4.99 repeating. So because of that, we had to make an accommodation. I wanted to stay with the solution because I still feel like it's faster. I know LeetCode says this, but also I'm not sure. I mean, I guess I could probably analyze the complexity. Yeah, so it's O of 1. So it's like it's faster than the iterative solution, because the iterative solution would be O of log n. So I was like, okay, I'm trading the security of this working consistently, or the consistency of this, for the efficiency of it. And that decision is not really one that you could just make everywhere. There are cases that you wouldn't want to make this decision, cases you would want to. I chose this solution because the constraint limited the numbers that it can be, and I'm pretty sure this should cover all of them. It passed the test cases. I'm not fully sure if it passes every single case within that range, but based on the fact that it worked for 21,000 solution or test cases, then it probably does. But yeah, so that's the final solution I came up with. It's O of 1. It's constant space and time, or constant time and space complexity. It's yeah, it takes advantage of the fact that basically base to the x is equal to a can also be, well, not rewritten, but logarithms basically find you the exponent, while normally you would be finding a result. So you take in the result, which would be your n, and then you're using a base, and since we have a base being a constant of 3, you could just do log base 3 of n, and then check if this is an integer, because an integer would be a perfect power of 3. So like for 9, you would get 2 here. For 243, you would have to get 5 here. The floating point error only comes from the fact that logarithm returns a floating point, and that causes issues when you have something like 4.99999. So yeah, this logarithm property allows us to get to constant space and time, but it comes with the trade-off of insecurity. It is not as consistently working as the iterative solution, but that has to be evaluated on a case-by-case basis, where you have to determine whether that's a good or a bad trade-off. In this case, I believe it's a good trade-off. So yeah, that's the solution I was able to come up with. Sorry, I was checking the time because I have deep work in a second. So yeah, that's the solution. That's the time space complexity. That's the explanation for why I chose this over another solution. And yeah, that's basically what we do. We use logarithms to see if this number is an integer. If it's an integer, that means that it's a whole, like a whole number, basically. If it's a whole number, then we know that it is a perfect power of 3, because you can put an integer or a normal power into x to the number, and then that would give you the number that you currently have as n. I'm not sure if I'm explaining it right, but you know, like that's kind of the thing that's happening here. We're just like looking to see if this is an actual integer, because if it's a decimal exponent, then that means it doesn't fit cleanly into the power of 3's set, or the set of numbers that are in the power of 3. So yeah, I wrote this down when I was trying to understand it, because I was like, okay, maybe we could make an improvement, but at the same time, can you really improve this in Python? I don't think so, because I'm pretty sure this is implemented in C, So they have a consistent solution that's already working and it's in a lower level language. So it's probably faster than anything you can write in Python that would give you the equivalent anyways. So yeah, that's what I did. I was originally thinking of typecasting it. Like I said, the issue was the floating point error, so that's why I changed this. I didn't rewrite the notes that I wrote, so that's my bad. But yeah,